All right, so let's start the session on atoms. When you go to the website, which I will provide you with the link, you go to the teaching, then down somewhere, you should be able to find a document which explains the dynamic simulation of complex system, and that's atoms. There is a little bit of history and why using atoms is useful. Of course, it's a standard for automatic dynamic analysis of mechanical system. The software was developed, I believe, 30 years ago as a student project in Michigan University. Then it gained popularity. Many industries now, like car manufacturers, train manufacturers, airplane manufacturers, they use this software a lot. In aerospace, that's a very popular software and good skill to have. Okay. So for this project, remember your focus should be your capstone project, not this one. This is just a tool. You may use it or you may not. Okay. Do not distract yourself by one thing in capstone. Remember, your goal is to build the structure. First step, I told you to use joysticks to move it, right? It's more like a game things. 3 servo motors, so you move it by manually. And then after everything working perfectly, as a bonus, you move to the next step and work with like adding an interface, nice interface. Right? The goal is that structure. These are all tools. You may use, you may not use it. You may say, okay, this is too complex. I like to build things and see if they work or not. That's totally fine. Because you can spend your whole capstone project on this software, and that's not good. Right? Yes. Just gain some knowledge on it. Know that this skill is there. I suggest on your spare time, spend time. And then later, if you like to, or if you wish to continue your skills on this one, work on it. And anytime if you have questions, feel free to ask. So yeah, as you can see, this is like a simulation for a car. Of course, in my vibration class, I will refer to that a lot. This was a project that it cost the company who built these things, if they wanted to do the actual test with a human, it cost them a lot of money because they have to purchase like a cadaver, a dead body, each dead body is around 300,000. So they could wear the helmet and break their necks to see if the helmet works. But here, for like a small amount of money, I built this model for them. And again, it's not a simple system, but with atoms you can do it. Atoms can do like this is obviously you can see the neck has been broken, right? Any complex system we can build, as you saw in like at the beginning of this website, the internet allows. So like this mechanism, 3D mechanism that shows that, right? So there is a document here on the Atoms simulation. If it's called a step-by-step manual. If you download that things, you can download it, print it. So I suggest go through chapter 1 and 2, but if you have time, you can go through it. And this is after today's session, you can do this, but before that, probably you couldn't. So it is a step-by-step. It's just the way that I write it is somebody who has no experience with atoms. After somebody show them that this is how it works, like today's session, that's my goal for today, then they can follow the step-by-step, step 1, step 2, step 3, everything's by pictures. And if you successfully manage to build all these graphs and build all these systems, then you don't need to do the assignment, but if you do, then of course you learn more. Then this is chapter 2, of course, lots of spring and stuff, but the concept is the same. Then you will see over here we have like a mechanism rather than a spring. It's a slider mechanism. And then down at the bottom, there is more like complex mechanism, which, and then this here is more like contact and so on. Okay, so that's about it. Let me close that thing, close that one. And now let's run Adams. So Adams has, if you install it, it has lots of other things. We have Adams Flex, we have Adams Train, Adams Car, Adams Chassis, and those are like module that, let's say, particular application they use them. But Adams View is the base one, and in fact, with Adams View, you don't need any other, let's say, modules. But those other modules, it makes it easier because they have some pre-built, let's say, structure. However, like in the past, I just always use Adams View, and that was not an issue. So when we run the software, we will see a window pops up. We'll give it a second. And in fact, when you install the software, you may not need to install all the components. You just need Adams View and Adams Solver. So how does the Adams solve problems? It uses Lagrange equation. Minky's favorite.
Yes.
That's the base of solving even very complex problems. This is how the software works. So, let's see.
Could I interrupt a little bit, like by reading that? Like we discussed yesterday, it's about we have an interview with the manufacturing and teaching team to talk about how the user needs or we can put in our device, and also we schedule time for taking a picture of the location view where actually the device will place.
Absolutely.
To see the dimension.
Yes. Yeah, that's a good idea. You want it like this week or no? You can wait.
Yeah, we can wait.
No, we need it as part of dossier 1. So
Okay.
we'd like to get
That's a good point. So why not right after the like vibration class, I have a meeting. Like today, I have to leave the lecture very early, like 5 minutes earlier. I have a meeting at 12. My meeting finished at 1. So why not we meet at 1? Does that work for you? 1 p.m. One of you?
I think I'm gonna have to pass, but
yeah, it's fine. Like
Yeah,
we
as
don't
long as-
all have to
Yeah,
be
you
there.
don't.
Yeah.
All of you don't need
Yeah.
to do that. And it is in I6, so it is like 5 minutes walk from here. Probably how long do you need? You need 5 minutes to take photo, right?
Yes.
I'm busy from 1 to 2.
How long will we take to walk from there to swim?
From here to there is 5 minutes.
Oh,
5 minutes
I
walk.
can do it.
Are you sure?
Yes, we are on the same team in the 1 hour in the 1 p.m. lecture, so it's okay.
Okay. Because then the next, after that I have another meeting at 2:30, which takes until 4.
Just take picture and then
Oh,
very
right.
quick. Yeah.
Okay, so 1 p.m. then my office
Yeah.
over here. Yes.
Okay. Yes.
All right, so that's about it. Okay, when we open Adams, we will see new model, existing model, and exit, obviously. If you are working a file, then of course you start with existing model. Remember, when you create a folder to put all of your things there, save all of your files, there is, like, if the name of your folder is something like that, Adams is not going to accept it. And then you will see errors because there is a space here. So whatever name you choose, no space, no dash, like this one is wrong. Okay, this is wrong. It gives you an error because it treats this dash as a minus.
Oh.
Yeah.
Oh.
Crazy, but this little thing, sometimes you build something and you see why there is that error. And I've learned them by heart. So, training Adams, you build a folder if you like to save, otherwise you're going to save somewhere weird. And then here you select the folder that you like to save because you don't want to training Adams. So this is where I selected my folder here. All right. And then select a name. Do not stick with model 1 because soon you are going to build some other model and you get confused. Let's say we call it test 1. You can change all of these later, but you can decide at the beginning. Of course, we are working with SI units, so let's stick with millimeter, kilogram, Newton, second, and degree. But always you can change them, right? I will show you that. But when you have these things in your setup, then remember, if you are building something in, let's say, in SolidWorks, and you import it here, the very first thing that you need to do is to check the dimension to make sure that they match, right? Otherwise, you may work here with the miniature things, right? Because your scale over there was in meter and here is millimeter, and then everything messed up. Just a quick check, which I will show you. We can do that. And then be consistent for the units. Press OK. This is the main environment of the software. Of course, very quick visual things. Whenever at the bottom you see there is this little triangle. You see that little triangle? If you right click on those icons, it means there are more things there. For example, if you don't like this bluish, you can make it white. No, too light, black. Better, right? But let's stick with the blue. Match with my
Nice.
blue. This dot, if you don't like them, you can turn them on and off. All right. And again, there is a triangle there. You can open it, and let's say you want to have 2 views. Okay. So, but let's now stick with 1 view. Zooming. If you click on this, the one on the top here, it does the task of zooming for you. In and out. So if you click on this hand, it does the task of moving for you. And obviously, this is the rotation. So Adams is a little bit finicky. When you click on one icon, right, I click, it doesn't do anything for me. Look at the mouse here, right? The mouse, it doesn't do, I move the mouse, but it doesn't do anything until I press the right key and I hold it. Now it does the zoom, okay? So the same with rotation. I click on rotation, I come here, see if I move my mouse, nothing. And then, by the way, this software works better if you have a mouse. Right. Otherwise, your hands, you can with mouse, but doesn't software works. Right? So you need to hold it, hold the right key. And this is, of course, it's obvious. It's doing all the returning everything to the main view. You can have a top view, side view, bottom view, isometric view. All right. And then this is all the basic things. The one over here is just do the task of, like you see at the top, it's just select, deselect. If you select something, you want to refresh your window, just undo, do, and then this is, of course, saving. It asks you, are you sure you want to save it? And then, yes, the name of the file is test1, and the extension is bin. That's the extension Adams use. So if you want to open a new instance, then create a new model, you create that one. That's obvious stuff, right? And then, of course, file, you have here the save as things, import and export. You will need import a lot, and exit, of course, that's exit. And the rest are all there, you see them. Something that is important to pay attention is the setting. So again, if I click on setting, then I can come here and click on units. And this is where you can change your unit. Let's say you change your mind, and instead of kilogram, you like to work with pound. Or instead of millimeter, you like to work with millimeters. Remember, the size of the model is not going to change, right? Everything is going to stay the same, except when you run your model and then you plot a graph of, let's say, displacement, if you change from millimeter, it's going to be in meter. This is all it will have. You can change your unit several times during building your model. However, I suggest be consistent because you're going to soon forget that, oh, you changed the unit, right?
Yes.
Then you're going to have your input for motor, for example, instead of, let's say, the torque to be Newton meter, it is in Newton millimeter. You enter it as 300 Newton meter, but since you change your unit here to millimeter, you're going to mess up. So be consistent. That's my advice. However, you can change your unit. What else you need to know? Working grid, I will come back to it. At the very bottom, if you run a code and you like to stop it for some reason halfway, this is your stop. Some like little things that sometimes can be useful. You run your model, you don't know how to stop it because there is something wrong or you are in rush and you want to turn off anything. This is stop the model. Even if you run a model halfway and you stop it halfway, still it will show you the result until halfway. It's not that it's going to clean up everything. So far, good? Yeah. Seems obvious, right? All right, so, and then you see these little things, that's gravity. Okay, so that's gravity. Let's look at the coordinate that we have at the bottom, X, Y, and Z. So our coordinate then shows that the vertical coordinate, Y, is like the gravity direction. You can right-click on gravity, right-click and gravity and modify it. You don't need it, but just something to know. For example, let's say you like to test your model when there is no gravity for future. Maybe you do a presentation somewhere and say if people use these things on the moon and the gravity on the moon is different, this is how it's behaved. Or maybe one application of these things that you build is going to be for aerospace, and you are doing an interview with aerospace and you like to impress them. You say, okay, if we build this mechanism and let's say in a space somebody wants to use it, this is how it behaves. So you can set it to 0 right now. And then set it to 0. By the way, when something is yellow, it means it's something wrong. And if I press OK, it gives me an error of return to dialog box. Okay. So if, for example, I put a number by mistake, let's say if I put this number 0011. Oh, accept it. I just want to put something wrong. But anyway, if there is something not right, is unhappy, it's going to be that. See, our gravity is in millimeter per second. I go slowly because these little things, I know it's not very important, are easy, sorry, but they can be very important.
Yes.
Right? And you can change the direction of gravity as well. Let's say you want it to be, this one to be 0, but your gravity to be in Z direction because you like the Z direction more. Right? You like your setup to be like that. It's preference. You see, this is now X, Y, and Z. By the way, Adams used the term marker instead of coordinate. Marker. It's M-A-R-K-E-R. Marker. That's the name we use. A Cartesian marker. So let's undo and return back gravity to what it used to be. So I undo everything, so I return back to that. So this is all the setup and things. Now, let's go to the front view. Let's build a very simple things here. Just click on this sphere. Right? This sphere, I can, if I know the radius, I can click on the radius, but I can forget these things, which I prefer. So the first part, I click on the body, and then I have these solids. I click on a sphere, and then I click somewhere randomly, hold it and drag it. hold and drag. Good. All set. All right. So I repeat this part. It's important. Undo. So I have all these tab menu, the bodies, connectors, motion, force, elements, design exploration, logging, and many other things, machineries, right? So what you need at the beginning for a long time is bodies, connectors, like this joint and stuff, and motion, these three. You need these three a lot. Forces, maybe, if you add a spring and stuff. So bodies, so we have some basic body like sphere, box, rod, and so on. Then we have this part is all flexible bodies. Luckily for the mechanism we build, you assume everything is rigid, because then it gets to the finite element. It's not difficult. Chapter 6 of that document explains these things for future. And then you can join things, cut things, you can fillet things and other things. However, this software is not meant to be used for modeling. So that's why we better model things in SolidWorks, in CATIA, in other software, and then bring them in here. However, if we can build something in the software, it's better, it's more accurate. So I want your attention here. So let's say I want to make a sphere. I click on the sphere. Again, if I come here, nothing will happen. You see, nothing is happening. If I click somewhere and hold, if I right click, hold, and I didn't do anything, I just drag my mouse. Time to wake up.
Time to wake up, yeah. Same alarm. Yeah.
So I got this sphere, right? So if I rotate it, this is the sphere that I got. If I right click on the plane and click on shade, this shows in a nice shade format. But remember, shade always needs more CPU. It's nicer, but needs more CPU. Maybe when you have a complex mechanism, at the very end, when you want to run it to make a video for your presentation, because the good things about this software, you can make a video for your presentation. Because in your capstone, for example, in a month, you want to do a presentation in class, you don't want to run add-ins and it doesn't run and takes forever to run, but you just want to make a video and show the video. For that, you may just shade it, but when you do the analysis, the ugly, unshaded wireframe is good enough.
Can I ask like how to shape it again? Like
right click, shade.
Oh,
Shade wireframe. Or you just can use the letter S. Oh, it doesn't work. Cool. Anyway, so that's something like to work.
How do you make sure the center is on that plane again? Do you just
Okay, if I rotate it, it is on that plane, right?
like how?
This is how it works, right? When I select that one, nothing will happen, right?
Yeah.
I click somewhere.
Okay.
Since I'm on this plane, it understands it is on that plane. And if I drag it, leave it, it's gonna stay on that. Okay. So, but we don't need to stay in that plane. Let's say I make this part. Let's go to the shape wireframe so you could see. I don't like that it's selected green because it matches with the coordinate or the marker. Okay. You can right click and then change the appearance. See, appearance. Let's say instead of green, you want it to be blue. Oh no. Red, apply. Okay, so that's red. So another things you need to know, always add-ins give you hint. Like if you don't know what to type here, if you just right click here, always when you don't know what to do in a box, right click. It gives you some hints. Like here, for example, color. Then you see pick a color, browse a color from somewhere, or guess something. So it gives you like a guess option. This is guesses. So you see you have all these options. And maybe you go with magenta.
Cool, very cool name.
Yeah. All right. So that's the appearance. When I create a body, this is on the side. This is the history of things that we do. Right now, under connectors, there is nothing. Under motion, there is nothing. Under force, there is nothing, and so on, right? Because we haven't done anything there. But under bodies, there is part 2. Always be neat and try to rename things nicely. So because soon the model become complex and you don't know which one is part 2, which one is part 3. So how do you rename it? If you click on this one, or like when you rename a new folder or something, it shows something like that. But let's try it. Maybe call it a sphere. Does nothing. The way it works, you need to right click and say rename. Then each of this one you can rename it and then automatically change everything. So let's here. No, sorry, not the object. Okay, so maybe a sphere is not a good name. Let's just stick with part 1 or whatever you name. Select folder. Okay, so that's the name. You can select whatever name you want. If you open that part, you'll see 2 things or 3 things underneath of that part. So one is center of mass. You see that CM? So maybe that answers your question. CM. That's the center of mass for that part. X, Y, Z, it matches with X, Y, Z. But remember, they don't have to match these X, Y, Z. They don't. Sometimes when you, especially in 3D model, the X, Y, Z over there, there might be a different orientation. That's fine. Program is smart enough to realize. Center of mass, you can right click and modify it. You can change the center of mass, but this is all it is about. So, and you see this, the Z0. So this is, you make sure this is on a plane. You'd better not to change your center of mass. Center of mass, let program decide where should be the center of mass. Unless you use a weird material, the center of mass is different, but never ever change the center of mass. Okay, that's my thought. Program automatically calculate everything. And when you don't do anything, it gives you a warning. If you are happy with warning, you can clear it and close it. So marker 1, so that was center 1. Marker 1 happened to be exactly on center of mass. Marker 1 controls the position of a part that you create. All right. Remember, randomly I click on a plane, but let's say I like this part to be at the 0, 0, and 0. If I right click on marker 1 and say modify, right now it shows that it is at this position, but let's say I like it to be at 0, 0, and 0. Fine. So it is there. All right. So let's say I like it to be at maybe 100, and let's say 0, and then 100. Fine. Oh, did I forget the semicolon? Yes, I did. This is a semicolon. Apply. Maybe 100 is not very obvious. Let's put it 1000 so you could see what happened. 1000, 1000. Fine. Now let's zoom. See, it's not on the plane anymore. Why? Because Z is 1000, right? So anyway, you have all these options to take out. So far good. You're following. You see what happened. All right. Press OK. We have a part. We know its position, and it's nice and clean. So what will happen if I run a simulation? Like in reality, what will happen if I have a ball? Because of gravity, it's just going to fall. The same things that happens in reality happens in atoms. That's the cool things about it. So what you need to do, you go to simulation, right? That tab, the top. You click on that gear, and you say that I like to run a simulation maybe for 2 seconds. So that's the end time. This is important to pay attention. This is the steps. Remember, atoms solve problems numerically. So we developed the Lagrange equation inside, and then the Lagrange equations, they are all nonlinear. Unlike vibration course, atoms deal with the original equation, the nonlinear equation. And those nonlinear equations, they need to be solved numerically. Remember, when we want to solve an equation numerically, we break down the time to steps, like increment. So this increment, we decide how they should be. If I say I want to run it for 2 seconds and I want my increment to be 200, it means I want every second to be divided to 100 steps. So obviously, the bigger this number, the more accurate the result, right? Remember, it's a numerical solution. It's more like when you do finite element or other things, the bigger, the smaller the steps are, it's more accurate. However, it needs a lot of CPU. So I suggest again, for when you build a mechanism, at the beginning, you don't need to go with the crazy steps. But let's say you're happy with your model, everything is finalized. Now you want like the final things, and you don't mind to run the program for 1 hour, 2 hours. So you select a very large number of steps. As a rule of thumb, stick with 1,000 steps per second for now. So this is all we need to do. 2,000 later. Here it doesn't make sense because there is no equilibrium. But when we have a mechanism, we better always say start at equilibrium. Start at equilibrium, it means that you tell the program that if there is a weight or something, and then there is a spring or there is a mechanism, create that deflection in the spring, stay at equilibrium, and then run the program from that point for me. If you don't tick it, it means that you tell the program that, okay, whenever I say start, if let's say there is a spring and then there is a mass, then weight suddenly applies and then the rest continues. It's up to you to decide. And then reset before running, it means clean up everything that I've done before, because sometimes you build a mechanism, you run it, you stop midway, you come change something. If you don't click reset before running, it means you tell the program that you start from what I stopped. Right. So these little things, but those are easily, you don't need them for now. So there is no equilibrium, there is nothing before. If I hit run, so obviously it's just going to fall down, right? Now, very important things here. You may say, well, wait a minute, it is just a weight falling down and it is only 2 seconds. But here we are waiting for like 20 seconds. Yes. Remember, the actual time is 2 seconds, okay? That's the actual time that we want the mechanism to be simulated in reality. But the time that it takes on our computer depends on CPU. It has nothing to do with the actual time. See, it takes about a minute to run these 2 seconds for me. Right? And it highly depends, you see, it shows the progress, and it highly depends on our computer CPU and the step that I selected here. For example, here, and of course you can guess where the ball goes now. If I zoom, or maybe zoom in or everything.
Yeah, I was gonna ask that because
it goes like all the way down, probably somewhere. It takes somewhere there, right? So, but let's return it back. Okay, here you can return everything back by these things. reset to input configuration. And then let's go back. Okay. So now let's, just for the sake of test, let's say these two second, I want it to be like 100 steps. Zoom. So you could see move up. If I run now, this time is fast, right?
Yeah.
See, this is just for the simulation, but in reality, it is 2 seconds. So the result, let's say whatever in future we measure force, we measure velocity, it is based on 2 seconds.
Can I ask a question? Like, if we don't have like anything, a platform, is it gonna fall forever or like?
If you don't have anything, it's going to fall forever.
Oh, okay.
But if I build a platform underneath,
Yeah.
and it is on that document. Let's say I build a platform underneath. I go to the body, okay,
Yeah.
And then I like to build a platform. I click on this box, and then I click somewhere here. So gives me a box. Let's look at the 3D and see how it looks. All right, let's rotate it and see. Okay, this is not what we want, right? We want like a bigger platform. So box is part 3. Let's rename it so we don't get confused. Let's name this one platform. Okay. So this platform, again, if I open this platform, it has a center of mass. You don't touch that center of mass. It has marker 3. If I change that marker 3, which is at the corner, I can move these things. Let's modify it. And let's say I want it to be maybe a little bit outside, but I just want to show you. Let's say -100. Apply. It moves -100 there, right? See, it is -100 there. So in fact, you use that things to control things the way that you want. Let's say this one, you want to move it a little bit here, 500. So that corner things control everything, but I don't want it to be that down. Let's maybe again some actions there to 1000. Okay. And this is the corner that, like, you can imagine you hold that corner and you move things where you want to push. But now you say I like to control the size. So on this box under platform, on this box, if you right click, not that, right click and say modify, so you can now change the size. And remember, in Adams, the size is just based on direction. So don't get confused if you see a -1. It tells you that the size that I want is in X direction is 2,850 millimeters, right? Let's make it 3,000 and see what will happen. 3,000. So always look at this corner. You see that corner?
Yeah.
X. You say that from that corner, I want these things to be 1,000, 3,000, right? So 3,000. And then you say from that corner, I want in Y direction it to be -150. So Y is going up, so -150, it means it's coming down, but you can make it positive, it's up to you, right? That's my platform. And then you say in Z direction, I want it to be maybe 2,000. Apply. Right. So you have now that things there. Okay, are we good? Okay. So what will happen if I run this now? Can you guess?
Would the platform also start falling?
Yeah, exactly. Let's run it. Platform will also fall down.
Yeah.
See? Okay. So what we need to do, go to connectors and say lock this one. You see that lock?
Oh, okay.
We click on lock. When you click on lock, you have options here. You see the options? two bodies, one location. You say that I want to lock it between two bodies. Remember, in Adams, ground is one body, and ground is all this blue area on my screen. Sometimes it shows something. So what I'll do, so the program asks me, pick the body one. Right? And always remember, at the very bottom, Adams give you some hints. Can you read at the bottom? It says, select the first body. So we select the first body, which is the platform. Sometimes you may say, oh, why it doesn't select it, right? As long as your mouse is on that part, it's selected. So, but sometimes you don't have one part. You have several parts on top of each other, right? And it's difficult to select. So right click on it to make sure that you're selecting the right one. Right click, then it gives you what part you have. Of course, here we have only platform, and then we selected the platform. What is the second question at the bottom?
Select the second body.
The second body, of course, it's not that the sphere, is ground, right?
Yeah.
I click on somewhere on the screen, ground, done. What is the next question? Select the location. Where do you want these two to be locked? Of course, this thing's a rigid body, and it doesn't matter where we lock it, but let's select that corner. Okay. But if it was a flexible plate, it matters where we locked it, right? Right? Because if it was a flexible body, then it because of weight, it could deflect. Right? But here it's a rigid body. When I fix one point, it means the whole things are going to stay. Now, if I run these things, okay, this is what happened, right? Then this command passed through that one because we didn't yet tell the program that these two are, they can interfere with each other, right? They have contact. That's why in the Adams model, that the video that I showed you, I cheated because I didn't specify that these two parts are going to clash. They pass through each other. Because of the visual, people think that it's moving, which is more impressive. But in fact, it goes up to a certain degree. So how can I tell that these two has a connection? If I go to force, you see force. Right. So, and then this is what we need. Create a contact. Okay, so contact, I just want your attention for a minute. Contact always is between two bodies, right? Two bodies come to contact. Part one, part two. In Adams, it's called J part, I part. I part, J part. I part, J part. Second, when two things come in contact, what does it mean physically contact? Like, let's say I have a ball and it comes and hit this ground, right? That area that comes in contact, it's an area, right?
Mm-hmm. Yeah.
And that area, you can model it as a spring and damper, because there is like more like a spring and friction between these two. And it's not just a ball, it can be any solid, like even my laptop and this table. The contact between them is a spring. But that spring, of course, has a very, very high stiffness, so I cannot press it down. So this is where I need to do. I need to click and say, well, what is my I part? So I right click. Remember, whenever we don't know what to do, right click. Right click, and it gives me some hint. Contact solid, I say pick. This is my I part. And then I click here. Second one, pick. This one again to make sure. I click that. Box 2. Ellipse solid 1, right? That's the name that the software chooses. Remember, these are the names because we haven't changed them. You can also change those. While I was lazy, I didn't change them. That's why the name is box 2. So for now, you don't need to change anything because by default, the material that program chooses is steel. You can change it later to aluminum. I will show you in a minute. And based on that, the program select this parameter for you. However, later you may Google and say that I need a contact between, let's say, aluminum and steel. On internet, you can find these coefficients. But for now, leave it as it is, and then hit OK. Now let's see what will happen. Now, I hit run, boom. So the program gets confused. Why? Because these steps are very small. When you have contact, the equations are really nonlinear. And program needs sometimes to like you need to use the smaller steps. Let's use the smaller steps and see what will happen. Like a smaller step. So I change it to 1000. Now the program can calculate everything clearly. So it comes, hit that things, moves a little bit, like similar to what will happen, and bounce back and move. Right.
Cool.
And then you see it's falling off from that. So at the very beginning that you build your model, do not create any contact. Again, as I said, it makes the model nonlinear, it makes it messy. Do it at the very, very end, or never do it maybe. For this mechanism that you build. I'm just focusing for your project. For other things, yes, do it whatever you want. So you can look from the side view as well. Let's say you finish the simulation. Right? Let's run one simulation together.
Does it go up?
I guess there was an error maybe in the simulation.
Oh.
Again, that's as I said, or maybe it just was just the, let's try it again, the graphic, I guess. Because there is no way that it comes back, right? It goes there. No, it shouldn't come back. Or maybe it should. I don't know. In reality, it goes and fall off. So it might be just the error. So you need later try it, increase the step and see what will happen. Okay. So let's move on. And a few quick things here. If, each of these one, right? So far, we just create like this box. You realize that the center of mass, you whether or not to change it. Marker one, again, you can rename all of these because remember later when you have lots of parts, then you forget which one was marker one, which one was marker 5, and then it gets messy. But marker 1 at the bottom, like for the platform, is marker 3. They can control the position of that part, right? Center of mass we don't touch. And then here you have like this ellipsoid, and here you have box. If I right click on this box and say modify, sorry. If I right click on the platform and say modify, okay? So on the platform, then on the top one, not on this box. This box doesn't do anything for us. So on this platform, I can change the material. See, by default, it is a steel, but let's say I like it to be aluminum. So what I do, I say user input. And then user input, see, by default, because it was a steel, it calculated for us mass, Ix, Iy, and Iz, like the moment of inertia for a box, right? And you know how to calculate it by hand, but you don't need to because the software will do it for us. And if the shape is not symmetric, it also calculates the Izx, Zy for us. And you know, this matrix is 3 by 3, but it is symmetric. So for now, it is 0. We don't care about them. But if your shape that you have is not symmetric, you know, if you have a part, if one of the axes is symmetric, then Ix z or Ixy with that one will be 0. That's momentum. So this is the mass and Ix, Iy, Iz based on steel. But if I want a different density, I say, can you see density there? Mass property, velocity.
Maybe it's undefined mass by, and then you can geometry and density.
Okay. Oh yeah, 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 you're right. Geometry and density. Geometry and density, and then yeah, oh, I got confused. Geometry and density. Okay, yes, yeah. Geometry and density. Yes. Let's say it is not a steel, it's aluminum. You Google it, and it is 500. Based on that, show calculation for us. Density was not stored. Oh, because we need to go now to user input. Oh, because we need to apply.
Yeah.
Let's go back. Apply. Now show calculation. Yes. Did we change it or no?
No, no,
I
no.
think the density was for steel.
Oh,
It was reset.
it was reset, right? Yeah. So let's change the density to 5,000. And then we apply, and then we say show calculation. So this is now the mass. This is Ixx, Iyy, and Izz. So you can change other things as well. That's it. Okay, that was for the platform, right? For the platform, we don't care. For the part one, for the sphere, if I right click and say modify, so now this is my mass, the material, and everything, right? Instead of mass, I can also change other things. For example, initial velocity. Let's say this part, I like it to have initial velocity. Initial velocity, let's say on x-axis, I want the initial velocity of, remember this is velocity, right? On x-axis, I want a velocity of 1,000 millimeter. So it means at the beginning, I want these things to fly off 1,000 millimeter per second. Yeah, 1,000 is too much. 100. And if I want also rotation, for example, these things I want it to spin around y-axis by 500. It does it for me as well. So initial velocity and the other things that you can explore on your own. It's okay. Now let's run the simulation. So you see it moves there. Something is not right. It might be just my graphic or the computer, but for some reason I feel something is off. Check it out. Let's go even higher. So it comes there, it should fall off, but it doesn't. Okay, it might be just the contact that was not right, because it treated like that. I have to go and check something. Right. But this is how then, so far, let's summarize. You can create something, you can change its position, you can control its mass property, and you can control its size, right? Let's say the size of this sphere, you like it to be bigger. All you need to do is, you know how to control the size of that box, right? You saw we make it bigger. The same with this sphere. You can right click on this box and say modify. So this is, oh, which one, not platform, sorry. On this guy, right? Part one, modify. Or this is the radius that we have right now, which are the same in X, Y, and Z. So, but let's say the radius, I want it to be 200. If I apply, so it's more like a egg shape, right? Because if I make all of them 200, then it will be a sphere. You see, you have all these controls, so you can make it 300 in that direction. Okay, so anyway, you can change the size of something as well. And when you change the size of these things, based on its density, it goes and calculate all of the stuff for us. Yeah. Okay, so are you guys okay so far?
Yeah.
Following along?
Yeah.
It's I know simple steps, but it create a like a good setup for you. Then when I give you that other video, you can follow that with more details, and then use that document from that website and do the assignment. Right? So I just want to quickly show you a few other things, and then we'll be done. 5 new database. Do you want to save them? No. It's interesting whenever I run Zoom with Adams, it takes longer for Zoom to run. So I guess, Inchi, you tried some of these on your with your Adams file, right?
Yeah.
While you were teaching. You did or no?
Oh, yeah, I was working.
Okay.
My simulation works fine though.
Should work
Yeah.
fine.
Yeah.
And you guys can help each other.
It says here, select zone port with which you would like ACF files on this machine.
Oh, I see. So you got it from the company or no, from this software from Inchi?
He like put a
Grab
zip
one.
file on, and then I just
Okay, you couldn't install it, right?
Oh, I can tell you later how
okay.
to install it. Yeah.
Yeah, there might be something, I guess, with that one. So if you click next, what will it say? Yeah, Inchi, come here. While these things is figuring out.
It's like a 3D version of the work model 2D. Yeah.
Oh yeah.
Yeah.
3D version, but no, it's way more
Yeah,
advanced.
accuracy. Yes, for sure.
accurate.
If you
Or maybe you guys can do it later.
Yes.
All right. Okay, let's continue. I go with a new model. Let's say select my things, select the name. Okay. Yeah. So let's quickly build a mechanism. So a link. This is a link. I click on a link. Let's say I select 0, and this is one link here. So this is in fact a 3D link, but it is on plane for now. We keep things simple and it is on plane. This link is here. This is part 2. I can rename it and call it link 2 or link 1, whatever we like to call it. All right. So this link, again, I open it, I can change. See, now we have 2 markers, marker 1, marker 2, because it's a link. And we can change the position of each of these 2 points. All right. So you have the control, let's say marker 2, modify, marker 2, let's say, still you want to be on the same plane, but this is right now minus 200 in X and 200, let's say make it 250. Apply. So, all right. You can change the dimension of this link as well. Again, modify. So this link, its width is 28 millimeter. You can make it maybe 20 millimeters. And its depth, right? Going to the screen, let's make it maybe 10 millimeters. Or it's up to you. So this is the link. So you have the control. You can change its material. So it calculates for us the IXX, IYY, because in Adams and in all dynamics simulation, we need all these momentum inertia and stuff. So that's one link. Let's create another link quickly. So let's say the other link, I wanted to start from there and there. Right? You may say, okay, how do we know that these 2 are matched? So we can do a quick things and modify them to make sure. So marker 2 was for this guy. If I click and say modify, it is minus 200, 250, and 0, 0, right? And this one, rename it to link 2. Okay. And this link 2, this is marker 3, right? That control that if I say modify, it is minus 200, 250, and 0, right? These two are matched. Like even if you, when you click, you don't click exactly at that point, click somewhere else, you can bring it back, right? Like let's say if it was somewhere at 200, so you want these 2 points to be the same location because you like to make a mechanism out of that. Let's shade these things so you can see what is there. So now these things, if I run it, you know what will happen, everything falls off. Let's connect them together. So I connect, this is the connection with this joint. I connect link 1. Let's right click to make sure we are selecting link 1 to link 2. See at the bottom, it asks us what to do. And then it says, where do you want these two to be linked? We want them to be linked at this marker, right? Again, it's difficult to select which one is which. You can right click and it shows you all the options that you have. And you know it has to be marker 3. That's why renaming is important. Now, I remember it was marker 3, right? But if you don't, you should rename it. So these two is being linked there. So what will happen if I run a simulation? Let's quickly run a simulation for 5 seconds, 500. So nothing special, it's just going to fall off. Let's connect the link 1 to the ground at this point. Now you can guess what will happen, right? If I run, so it's going to be like that, right? And you can get all this cool motion. So let's say you want really to, rather than this one, you want to make a, so Minchi, it was like the motion was like that, right? But let's say you want to make a mechanism. So let's add another link. This time, maybe this link go all the way down here. So let's connect them. This link, let's rename that one. I like to be organized. Go to body. Oh, whenever you want to like go back to your original things, if you click on that things, you return back. Okay, let's select, clear the selection. The escape doesn't work. So it was rename. This is link 3. Okay. So, and then let's connect this link to link 3 at this point, and this link 3 to the ground at this point, right? Now we have a 4-link mechanism. Let's see what will happen if you run them. Whoa, that is like a crazy thing, right? But let's say this is not what we meant to build out of this mechanism, because this is all moving because of gravity. Let's say I like to attach a motor here, so these things rotate. I go to motion, all right, go to motion, and then I have 2 types of motion in this world. Either we have translational motion, we push something or pull something, or we rotate something. So this one, since I need a motor, I want a rotational. The second one, I select the second one. So you can read the question at the bottom. Select the rotational or cylindrical joint. Remember, whenever we have a motor, it has to be a joint somewhere, right? And let me rotate it here so you could see. Remember, we are started with a 2D model, so I could explain, but this software is meant for 3D things. So everything is 3D, in fact. So you see, this joint is like real life, it's 3D, right? And by the way, this joint, you can find it under these things, like, and you'd better rename them as well, because later you need to find the forces in this joint. And this is joint 1. Joint 2 is somewhere else. No, this is joint 2, sorry. This is joint 2, because when you click on them, it will highlight them. Okay, so this is joint 1 at the top, joint 2, joint 3, and so on. So joint 2, you can change its color, you can change its name, and so on. All right. So what we want to do, we want to go at the motion. Click on the motion, and then the question asks you to select a joint. And this is where we like the motor to be. I just click that one, and that's the motor. That's it. So that motor now, if I right click on it, I can modify it. I right click, it's called motion. You can rename it, it's under motion, right? Motion is not a good name. Let's rename it to motor, for example. Motor, and then hit OK. So this motor, if I right click on this motor and say modify, so motors, they have a speed, right? So you can select angular velocity if you know the speed, or angular acceleration, but always I suggest go with displacement. Let's say you have a motor that runs with a constant speed, which is usually the case. But later in your analysis for this sphere model, maybe you like to see if the speed is not constant. You can change all that function. But for now, for simplicity, if let's say the speed of your motor is 1 rotation per second. So omega is then 1 RPM, right? 1 rotation, sorry, 1 RPF, rotation per second. Okay. So remember, 1 rotation is 2 pi, or 300 degree.
Yes.
And remember, at the beginning, the unit that is selected was in degree. Okay. So D in Adams stands for degree. If I put here 306 degree, what it means for me? And remember here, I selected displacement. When we have omega, what is the relation for theta? Displacement? Omega t, right? If omega is constant, right? So, but if you have acceleration, it is half of alpha t squared.
Yes.
You can put any function that you want here. Okay. And a square, by the way, here for Adams is star star.
Oh,
It means power 2,
like Python.
like Python. For a long time, I thought it has to be 2, but it gives me error. And then I was unhappy. I didn't know what to do. Then I realized, oh, it is a star star. Okay. Anyway, you can have any function that you want here. But for now, let's say speed is constant. Okay. And what it means to you, 360 degrees multiplied by time.
1 revolution
Per second, right? It means if time goes from 0 to 1, my mechanism is going to rotate 1 complete revolution. Okay, because remember, set always this one to displacement and put the function there. It is smart to, if you select velocity, to just put velocity there. So now it knows its velocity is 360 degrees per second. But I suggest always go with displacement. There is a reason, because in Lagrange equation, we take the derivatives. When we have the displacement, the program can take the derivatives and deal with the errors. Right? It's more accurate result. So there and there, and then I apply OK. So let's now run it and see what will happen. So I set it, let's for now set it to 1 second. And we expect 1 second to have 1 complete revolution. So the motor runs. Oh, it gives me an error. Why? Because this mechanism, right? This mechanism probably cannot do 1 complete revolution here because of the size of the link. Because they have to work out, right?
Right. Are we able to change the direction of the revolution?
Even that one is gonna stuck somewhere. Yeah, you can. You just put a negative there.
Oh, okay.
But you know, there is a fundamental issue with our mechanism.
Right.
And that mechanism, the size, you know, 4-link mechanism, see the change, the direction change, but it's probably going to lock somewhere there. See, it's going to lock there. So I wish I could. Let's delete this one. Oh no, let's not delete it.
Can we just remove the link?
No, no, I'll make it bigger. Let's make this one bigger and see if it solves the problem. Marker 2. Oh, you know what? Let's do something. Let's get rid of this link. In 3, you can right click and say delete. And it asks you, do you want to delete everything, including the join? You say delete all. So everything has been deleted. Let's body. I guess if I make this link very, very large, then the mechanism can work. Maybe we should have some size or something. Let's try that one and see what it will. So you guys had Minky, I know, had the machine dynamic, but you guys had dynamic. Probably you've seen mechanism before, right?
Yeah.
Except Minky, I get the rest of you have. Anyway, Minky can explain to you. So for link mechanism, you cannot build any for link mechanism and expect it works. The length should be in a certain size, so it will work. So let's try now this one. Let's see the mechanism really reasonable. So my guess would be bigger. Oh, I should have. 700. Oh, yes. No, other than that one. It should work. I should have maybe used one of the textbook, which gives me the size. Let's now try this one.
The first one just need a bit longer.
First one?
Yeah.
Want the motor? Or shorter?
Link one a little bit longer.
No, I don't think so. Even shorter would be better. Let's make it shorter. So link 1, we get rid of link 1, let's say. Let's try a shorter one. But later you can use like for link mechanism in
Is there some sort of like function in Atoms that just calculates the perfect size?
no.
Okay.
Yeah, it just tell you that do your own design and come here and just tell you what is the size.
Yeah, that makes sense.
Motion, this is the motion. Modify motion. 360. Hey, success. Okay. So this mechanism now works. You see, the problem wasn't Atom. The problem was like that we have to have a right size. Like if you built your sphere robot, okay, in Atoms, and if those intersections, they don't intersect at one point, the mechanism start working up to some point and then stop and gives you error. It says because it says that in practice it's not possible. The same here. If you build this mechanism, it's possible to run it, That's why like the geometry works fine. Okay, so 360-degree here. This is the speed that we set. So if I run it for 1 second, you saw it revolve for 1 revolution. If I run it for 5 seconds, so it's going to have 5 revolutions, right?
So cute.
Yeah.
Oh,
And you can change the speed. So let's say go super fast. Let's say 10 revolution per second, right? And we run it.
It's gonna be wow.
It's gonna be wild. All right. So now one last thing that I want to show you. So you see what happened here, right?
yes.
Try to work like that so you understand what's really happening. Now, if you put these things 360-degree, you know it is 1 revolution per second.
Yes.
If you change that coefficient to, you know, it is your speed is 2 revolution per second. All right. So I run the simulation. I'm happy with the simulation, but that's not the point of the software. The point is to get some numbers, right? For example, we like to know how much power this motor used because of the weight of all these links. These links, they have all weight, right? They're made out of steel. They have, and the joint, they can have frictions, right? Each of these joints, if you go to connectors, let's say joint 4, let me zoom so you guys could see. Okay. Joint 3, somewhere there. That's why renaming is useful. Joint 4, whatever joint is. If I modify that joint, I can select friction for that one. Right now, its assumption is there is no friction. So I click on mu n, and you say what is your coefficient, like mu static. Remember here, because it's a dynamic, you need the dynamic, mu dynamic, and mu static. Okay? Which mu dynamic usually is smaller. You just Google that, what is the friction between aluminum and aluminum, or aluminum and steel, and then you put it there. Right? The rest of numbers, you leave it as they are. So, but for now, no friction, nothing. Okay. So we run the simulation. Even you can add forces to this mechanism. Let's say if I go to force, I can apply load. Let's say these things, there is some force somewhere, or maybe there is a spring. Let's say there is a spring somewhere, and this is the spring. Okay. This is the spring. You can right click and again modify the spring. So for a spring, you have a spring stiffness and spring and damping. So you can set them 0, or you can have a value for them, right? So maybe this is small, let's make it 1. Okay, so let's run the simulation for now and see what will happen. All right, so you see, this is the simulation. Okay, simulation is done. We go to the result. All right. We go to the result and click on that thing. So a new window pops up. All right. On this new window, now you can watch your result. That's the program, my program. Yeah, for some reason it's weird. Whenever I run Zoom and this thing, my laptop comes very slow.
So the new window is like in front of the atoms. We just a little bit of this window like half screen, and then we can see it now.
You don't need to do that. There is a better way.
Oh,
yes.
Okay.
Yeah, you can have 2 monitors and put one here, one there, or you can put half here, half there, but there is a better way.
Okay.
If these things allow, I don't know why it takes, okay, eventually. All right, so this new window, which is the result, you can go back and forth between this window and the previous window. I don't want to do that because it's going to take forever. So this window is for your result. you can check whatever you want. You can check the forces in the joint. You can check the velocity, the motor power, whatever you want is here. Whatever that you can think of is here. All right, this is how it works. And I want for 5 minutes your attention, then you have time here to do the things that you want. First of all, this window, you can split it to more windows, so to see more things. So if you click on that one, right? Maybe for now, I click it to 2 windows, left and right.
Takes a while.
Yeah, I realized it last time I was doing something with Zoom, and I realized that whenever I run Zoom with this software, for some weird reason, it takes forever. But on your computer, it shouldn't take that long.
Yeah.
Oh, nice background.
Yeah, I don't know. I think this just shows for student edition or something.
it does.
Yeah.
Oh,
I don't know how to delete it. It's a bit annoying when I was making the models.
This software is super expensive.
Oh, it
It's
is.
a range of like $1 million. But
Oh,
even a
wow.
company that 2 companies that I meet the software for them, they afford to rent it for like a month. That's why
Wow.
the student version they put that things,
Okay, yeah.
and also they I guess you are limited to 20 parts, so you cannot build a mechanism that is more than 20 parts.
oh, 1 million for buying this software.
Sorry,
So $1 million for buying this software.
if you want the entire modules, yes.
Oh.
Even you received up to 4 years ago we got this software like every year. We purchased the software with discount. Then UBC, yeah, nobody, because I left UBC industry, nobody used it. Recently, they said, okay, let's see if there is enough people to use the software. All right, so we break down the window to choose. You have other controls that you can do, make it smaller, bigger, you know that things. So if I right click on one of them and say load animation, my mechanism comes here. I can resize this mechanism to fit everything if I want. Like I can, for example, click on this zoom, and zoom these things. All right. I can move it. If it is 3D, I can rotate it so I can see it in 3D. All these things are possible. Let's make it cooler in 3D. Okay. So the rest is for my result. If I click here, so let's start with maybe link 5. Part 5. I don't know which one because we changed a lot of things. So one of these links, let's say I want its center of mass velocity in X direction. I add curve. So this is the curve that I get. So now if I click on the animation one and I hit these things, you'll see it shows the motion. It shows also where it is. If while the animation is being done, if I hit record, it makes a video for your presentation. Right? But you have like go to record as well, select a name, change these things to a better quality, but do not go over 75 because then it takes forever. The frame rate and those things, you can play with all those things. But let me show you quickly more results. So you are not limited just to this window. This now has been saved. You can create a new window, a new page. So that's the new page. This one, let's right click and say instead of animation, load plot. Might takes time, but what I wanted to show you is while it's thinking, you can for each part you can plot their position. And you have other things. It's not just the position and velocity. You can plot the forces and other details. Get these things running. Okay, this is here. All right. So this is for animation, this is for plot. I don't want to click on that one anyway, but it doesn't have to be animation. Like it can be just one window, right? And all plot. So let's see what we have here. You see here, if I click on body, I can see only the bodies that I have. Part 5, part 4, and link 2. I can, for each of them, I can add their motion in X, in Y direction. I can plot the acceleration, the kinetic energy, the potential energy, whatever I want for this part. I can clear these plots. I just click on this area and say clear plot. Okay. Let's say I want the forces. So the only forces that we have is this spring that we added, right? So for this spring, let's say I want the formation, like I want the force as a function of the formation. So that's, it gives me based on time, but I can get it based on the formation. Constraint, if I go to constraint, let me clear this one. If I go to constraint, let's say for joint 5, I'm interested on the forces that applies on joint 5. Again, this is useful for you because you, at least for your like capstone for your documentation, you need to do some calculation, right? Show that you calculated the forces for bearings, all those bearings, right?
Yes.
And remember, we had all these bearings here in this example, right?
Yes.
We had the joint or bearings, which are the same. And if I calculate element of force and the magnitude and curve, so this is the element of force, of course, because it's a rotational things. So now from this, I can realize that my magnitude of force is maximum is around 27,000 Newton, right? Which was large because we had like this crazy mechanism. We didn't pay attention to it.
Is it available to show what's the exact number?
Yes, you can somehow here, right? Yeah, data here. You see, you can export this.
Oh.
You see, it's no, not that one. Let me find it and I will show you.
Okay.
It's somewhere. Care one. Select. T4. It's somewhere here. It's been a long time that I haven't used it. Anyway, it is on the document that I put it there. For you.
Okay.
Yeah.
Check it.
Or you just play with this. You can, if you click on info, just give you some general information.
Yes.
And then save to file, save that one, read from file, no. Anyway, so yes, you can read the exact number and get those, move them to for your report. If you click on these labels, right, on this axis, sorry, on this axis, you can change the label here. It is label like time, font size, and many other things you can do. What else I can tell you? You guys, okay, let's spend 5 more minutes and then we'll do one more thing. So is it clear so far what we did here? Okay. So remember all these things that we created, they save there. Like if I move back on this, click on this page, my previous things is there. So you can create as many as possible that you want for those things. And then if I click on that one, I'm returning back to the main page here. Sometimes, okay, so this is what will happen. Okay, on this animation, when I run this simulation, so it moves and I wait until it's done and I go and check the result, right? But it may take long time for this simulation to finish, and there might be something wrong, and we wish to see the result as it's running. Right? We like to have like a sensor, maybe on one part of these things, to tells us where it goes.
Yes.
Okay, this is a nice thing to have. We can add sensor to these things. How we will do that? So this is how we will do that. We will go to design exploration. Okay? And I'm just going to teach one of these things to you so you can explore the rest with you and check that out. Design exploration, if I click on this caliper, what it says, create a measure. Okay. So I click on that one, this new window pops up, and click on this plus sign, because the name of our file was model1, I didn't change. So it tells me that I have all these things to measure, tells me what I'm interested in measuring. Let's say I'm interested in part 4, and then I open part 4. It tells me that for part 4, you can measure, for example, something related to its center of mass. Let's click on center of mass, double click on center of mass, new window pops up. So it tells me that this is your part 4. This is center of mass, right? And it tells me that what do you like to measure about this center of mass? I say I like to measure its displacement, but I can measure its velocity, angular things, forces, or whatever that makes sense. Right now, for the center of mass, the only things that make sense is to measure its displacement. Do I want it in X, in Y, or maybe in Z? In Z, of course, is in plane, it's 0. So we can click on magnitude. And click on magnitude, it means the square root of X and Y, right? We want it in Cartesian, and then everything's done. Click OK. It's done. We are done in 2 minutes. For you guys, should be fast.
Really useful.
Right.
Yes.
So anyway, this one, while it's working, you can, while your program is running, you can add as many sensors as you want to measure the motion of different points, to measure the force for different joints as it's running. Right? So you can, but you don't want to make your screen very too much data. All of these things again are available later, as you saw, but this is for while we are running it.
Perhaps about based on your experience, like which element from this chart is more useful to a torque or velocity or acceleration?
So for the
3D, the spherical.
Oh, for the 3D spherical, the torque is important. The power is important. This power was there, right?
Yes.
If for one element the power was not there, because torque is there and the omega is there, torque multiplied by omega gives you power.
Oh.
And then you look at your graph and you see, oh, the maximum power that I need is, for example, 100 power.
Okay. Thank you.
So see this graph appear here, guys? Right? Now let's run the simulation. This is from the previous one. So click, clear everything, and then run. See, this graph is start from 0, and as I'm running it, it shows the position of center of mass for me. See, it's very useful to have it while the program is running. It's like a live measurement.
Yes.
Besides it's being super nice, it also sometimes gives us some good information while we are running the program to stop it. And it's not limited to just the measurement of the displacement. Again, if I go to design exploration, this caliper, it gives me a bunch of data. But let's say for some weird reason, Minchi is interested in measuring the distance between this point and this center of mass. Okay. Then you can create your own measurement. You click on this one. You see, create a new point-to-point measurement. If I click on that one, and I say I like to measure displacement, the magnitude of displacement, I click on advanced, and it just tells me between which 2 points. I say from point, right click, pick, let's say this point. Or let's just go for guess for now, but you know, let's say we rename them, we know which is marker 23. Because remember, you have a choice to pick and go and let's say find it and pick it. Let's say right click here, it doesn't show me.
Double click.
Yeah, or you just say guess, for example, marker 16. I don't know which. But let's go for that. The magnitude. Okay. So then the caliper up there, it gives you the choices that you have, the forces that you can measure. The one at the bottom gives you the choices from, let's say you like to measure a distance from one point to another point.
Oh.
And there are other options as well, but you mainly need with these two. All right. So we're done. I will, tonight, I will put these things in the sync. But after I put it there, you can cut it and put it somewhere else, because remember the sync folder that you have is limited to 3 GB.
Yes.
So this video by itself will be 1 GB.
Yes.
You want to clear up, but it can stay for a while, so all of you guys could access it and then delete it from there.
Or maybe I can just like upload it to our Google Drive.
Or yes, to your own system. So plus this video, I will post video number 2. That one was like start with the beginning of this session, and then it add more details, which is more relevant to your spherical robot. I also add another video, which is very similar to today. That might be useful, because in that session, I might add extra information there. So I suggest watch these 3 videos, do some simple practice, try to create at least this mechanism before going to 3D. Because one of those videos explain how you can do 3D. Let's say this is spherical robot. And also it explain how you can import part from SolidWorks. Yeah, you're not in rush. You can work with these things. And since we are here, you guys have class, I guess, right? Also mine.
My first is your class.
At 11?
Yeah.
Oh, okay. But I have a meeting, so let me just another thing that I suggest, play with that file that I put for you. Just play with it a little bit. Open it and make sure that works. So where we put it? Okay, it's here. It is a spherical robot. Adams copy. Let me put it on desktop. I don't want to damage that file. Let's just quickly open that file. Okay, file. Open database. Do you want to save it? No. Well, let's save it for you now. Cancel. Let's close that thing. I will save this one for you, and I put it in your things. Okay, Michi?
Yes.
You like this model if you like it.
Okay.
And file, new file, open database. Do you want to save the database? Not yet. So on desktop, spherical robot, this is the file. Let's open it. Let's stop sharing. Okay. Meeting.